11.2.1, using complex numbers and the complex plane. Now, just to get you good and warmed up, there's two types of complex numbers. There's the standard form, which is what we're going to begin with down here, which is thought of as a plus bi. Now, it's just a different way to give you a different type of coordinate point. But we'll talk about that. But then there's another one, and that is r cosine theta plus I sine theta. Now, you want to write that down. That'll be helpful. So they're going to ask you, put your answer in standard form or put your answer in polar form, which you will also see other books or lessons called trigonometric form. In this book, they're going to use polar form a lot, but this is also something you can substitute for that. So, with all that being said, let's start with the easy ones. So you can see that it starts out with complex numbers are graphed on a complex plane, shown at the right. Let's stop right there. So, I guess I could I got two pictures that I could use. Oh, I see. So on this one, they gave us a dot, and they're asking us, what is that dot? Well, you see the x-axis, which we're used to, is a real axis. Now what gets changed is, this is now your imaginary axis, which is really kind of strange, but that's your y-axis replaced with imaginary numbers. And that's all it is. So what is that number? Well, from the origin, I need to go to the right 4, so that would be 4. Now here's the difference. You guys are used to plotting this point, like let's say you had the old axis, x and y, and you were going to plot the point 4, -5. You'd go from here, 1, 2, 3, 4, 1, 2, 3, 4, 5, and that's where your point would be. That point is 4, -5. Now, if I asked you guys right now, what's that point? You guys would go 4, and then, even though this is new, this is your imaginary axis, so this is really 2i, 4i, 6i, -2i, -4i, -6i. So, with that being said, that would be down 5i, -5i. But as you can see down here, and here, and here, and little hints up here, well, there it is right there, you've got, this is how you actually write this. So this is not really wrong, it's just how you're going to think of it, but you're going to rewrite it as 4 minus 5i. This is a point in a complex plane. Complex just means it's different. Now this is an imaginary axis. So that's how you would write it. So let's practice this idea. Plot these 4 complex numbers. Well, 2 minus 3i, your brain would probably think of it like this. So we're going to go out the x-axis, the real axis 2 units, and then down 3, because that's my imaginary axis. So there's z1. So that's what they called it. 1 plus I. That's just 1 to the right, 1 up. There's Z2. This is a little confusing because you're like, that's only one thing. Correct. So that's 3 plus 0i. Same thing as 3, 0, if you want to think of it that way. So we go out 3. We don't move up or down. This is left 2, down 1, because there's a little invisible 1 there. Left 2, down 1. Oh, I'm supposed to make this Z3, and this would be Z4. Okay, up to example 2. Introducing you to a new word, modulus. Modulus is just another word for distance. So this will all make sense as we do a few problems, but it also is the length of your radius, or in my class, it's the length of your spinner. And we don't get away from this in trigonometry, so the spinner is always there. This is just another representation for modulus. So when you see this symbolism, it's not the absolute value of z, it's the distance. So we'll talk about this. Now what is this? Well, to be honest with you, if you have a triangle like this, we got A, we got B, we got C. If I said, hey, A squared plus B squared equals C squared, we're like, what is C? We take the square root of that side, we take the square root of that side, and that would give us that formula. So this is nothing other than the Pythagorean theorem. Now we've got this little guy over here, and it's a real helpful hint when they ask us for this thing called the argument. Now, we will talk about what in the world that means on a few of these examples. I know this is pretty small, but it says plot each of the following complex numbers on a complex plane and state the modulus and the argument of the number. So that number is an a plus bi thing. That's a complex number. Record your strategies. All right. So the first thing we're going to do is take our new axis, where this is x, this is I, and we're going to go left 3, 1, 2, 3, up 4, 1, 2, 3, 4. They're going to start you off with this nice easy one. Now that's a point, but really what it is it's the point on the end of the spinner. So, which I say spinner, but it's also the radius, and I could also say the hypotenuse. So this is -3, this is 4. What's the modulus? The modulus is its length. Now you guys might be saying, well, they made it seem all fancy. Well, this is new language, new symbol, old school formula. So we could go a squared plus b squared equals c squared, but remember the hypotenuse is always positive. It's never negative. It's just a spinner. And you can go, geometry class, 3, 4, 5. So there's the modulus right there. Now what is this thing? The argument. The argument isn't just the angle. It is how far you spun your spinner to get to that angle. Now how do we find that angle? That formula. Now you don't have to use this formula if you have all three sides. You could use sine, cosine, tangent. But let's use tangent. Tangent of that angle is opposite. That's not a negative. I just made a little mark there. Opposite over adjacent. TOA. So now we got to go second tangent, then type in 4 over -3, and that will give us our theta. So let's turn this thing on. Second tangent, 4 divided by -3, enter. So notice what this says. It says -53 degrees. Now, this is very confusing when you first start doing these problems. You're like, that doesn't look like it's a -53 degrees. Well, here's the thing. When you type in tangent is negative, your calculator knows that all students take calc. What quadrants is tangent negative? Well, not this one and not this one. So your calculator doesn't know whether your math problem has landed you in the second quadrant or the fourth quadrant, so they plunked you into the fourth quadrant. That's a -53.1 degrees. You need to realize that, there's a different picture. If I just extended the same line, if this is -53, this is +53. So what I'm saying is, that guy right there is 53.1 degrees. Now, that's still not what the problem's asking for. This is the argument. So how do I figure out how far the spinner needed to be spun to get here? We're going to go 180 minus 53, so it's 126.9 degrees. There it is. Now, I don't want to chew up all your video time, but if I said cosine of theta, and I went adjacent over hypotenuse, and I tried going like this, second cosine, just to show you something, second cosine, -3/5, enter, and then I get right there 126.86. So this is more of a direct approach. So again, you can use sine, cosine, tangent, but you got to know what quadrant you're in. By just knowing this point takes you into the second quadrant. Let's try this one. So this is telling you, plot the point. 1, 2, down 1. So there's my spinner. This is -2. This is -1. Now there is no 1, 2, 3 family. So I need to go a squared plus b squared equals c squared. Well, that's 4 plus 1, which is 5. So I take the square root, and all I'm doing is this formula right here. And so that's the square root of 5. So what is that? That's the modulus. Now they want the argument. But we got to find this angle. Let's formulate a plan, and then subtract, and then add that to 180, and it will take us there. So we got to find that. But let's see if the calculator just gives us a direct path. I doubt it. Let's stick with tangent. So tangent of theta in this situation would be -1 opposite over adjacent over -2, which is just the same thing as positive 1/2. So second tangent, I'm just going to go 0.5, 26.6 we'll call that. So this angle measure right here is 26.6. So if that's 26.6, and I'm trying to figure out how far to spin the spinner in a positive direction, that's another thing I haven't said yet, I need to add 180 to that. So that'd be 206.6 degrees. And the one thing I need to really emphasize here is your argument is going to be greater than 0, less than or equal to 2 pi. They might flip this on us. All they're saying is they realize that there's an infinite number of spins you could do. They just want you to go positive, because there are no negatives in here, and stay within 0 and 360. So that's what we've done. This one's so easy, it's hard. So what is this? Well, this is the same thing as -5 plus 0i. So I would go here, and I'd go 1, 2, 3, 4, 5, and I would stop, and that's where my spinner stops. Well, what's the modulus? 5. How far did I spin it? 180. Don't need a calculator for that one. So there we go. Pretty simple. This one, similar to C, but now we don't have the constant. So we start with our drawing, 2i. So that means 0 plus 2i. So we don't go to the right or left, we just go up 2. And there's my spinner. Well, what's the modulus? Well, spinner's got to be 2. How far did I spin my spinner? 90, or pi over 2. Okay. Getting towards the end of this lesson, but now we've got this thing called the distance formula, which, remember, what does the Pythagorean theorem give us? The distance of our hypotenuse, which is the modulus. So the distance might be a different way of finding it, but in this case, look at this question. How can the distance between two complex numbers be calculated? So we're going to need the distance formula for this sort of a question. I think that might be a mistake, because this is how to find the distance of the hypotenuse of one spinner. But let's put that on the back burner. I might delete that in a second. Let's just follow this. Maybe we'll need it. Oh, I see. We'll need it down here. Write an expression to calculate the distance between them. So what we're going to do is actually just I mean, there it is. Write an expression to calculate the distance between them. It's our distance formula. But let's actually practice a problem. What is the distance between u and v? So the first thing we better do is take a look at this. 5, negative 4. 1, 2, 3, 4, 5. 2, 3, 4. So that's really 5, negative 4. So we can now take this back to our world that we're used to. Even though this is negative 4i, it is 5 to the right, down 4. So we're going to connect this to the old stuff we used to do. And 3 plus 2i. 1, 2, 3, 1, 2. So this is 3, 2. So here's my x1, y1. Here's my x2, y2. And if we plug it into that formula, x2 is 3, x1 is 5 squared, plus y2 is 2, minus, careful of those double negatives, squared. So, takes a little while, but this is negative 2 squared, which is 4. This is 2 plus 4, which is 6 squared, is 36. So we get the square root of 40. Now, I noticed the Pre-Calc book doesn't break these down very often. So it's the square root of 40. But if they do break it down, it'd be square root of 4, square root of 10, 2 square root of 10. Now, u minus v. Just so you know, just like any number in math, you can subtract. But this is saying take u, 5 minus 4i, subtract all of v. And here's the twist. You got to insert parentheses because we want to subtract all of it. So this is actually 5 minus 4i minus 3 minus 2i if I distribute that negative through. So 5 minus 3 is 2, negative 4i, and negative 2i is negative 6i. And there's my answer for letter C. Now this says evaluate the distance or modulus of u minus v, because this is my answer for u minus v. So they're saying find its modulus. So 2, negative 6. 1, 2, 2, 3, 4, 5, 6. So remember, this is 2, and then, oh, that's the end of my spinner there. So that's 2 to the right, down 6, and now we're going to use Pythagorean theorem. A squared plus b squared equals c squared. That's 36 and 4, which is 40. Whoops, I already did the square root and everything. So you can see that they're the same, but that's it. Hold it. All right, example 4. How can the midpoint of two complex numbers be determined? Well, here's the formula right here. So we're just going to kind of get after it. Consider real numbers m and n. Write an expression to calculate their midpoint. Well, it's right here. That would just be m plus n divided by 2. Let's apply it to this problem. If u is 5 minus 4i, let's take a little picture. 1, 2, 3, 4, 5. 1, 2, 3, 4. Be right there. 5, negative 4. And this is 3 plus 2i. 3. And then 2i, so that's 3, 2. They want to calculate the midpoint. But they're saying add them together. So let's add them together. So u plus v, 5 plus 3 is 8, negative 4i, and 2i is negative 2i, and divide that by 2. Well, that would be 4 minus I, which is saying 4, 1, 2, 3, 4, down 1. And you can see it looks like it's right in the middle. Why? Because it is. So, not bad. Okay, so here's a lot of information. But what I want to grab from this is this right here. If z is a plus bi, then this looking thing with a little bar over it is its conjugate. So we got a plus bi. That symbol is just a symbol for its conjugate, which is a minus bi. So here's z, here's w, here's v. This looks harder than it is. But what is z times its conjugate? Well, z is 3, so I'm doing this one. Z is 3 plus 2i. It's asking us to multiply it by its conjugate, 3 minus 2i. Now, if you learn something here. When you're multiplying conjugates, I'm going to show you something. First, 3. Outside, negative 6i. Inside, 6i. Last, that'd be negative 4i squared. I want to focus on the outside and the inside. They cancel. And what is 3 minus 4i squared? Well, that's 3 plus 4. Because I squared is negative 1. Negative 1 times negative 4 is 4. So this would be 7. So what I'm saying is you don't have to do the outside and the inside. You can just do the F part and the L part when you're multiplying conjugates. Save yourself some time. Now I'm not going to do both of these just to save a little time. Let's tackle that one. V, which is the square root of 3 minus I square root of 2, times its conjugate. I know it's kind of blurry, but square root of 3 plus I square root of 2. That's all it's saying. And then we can just, what I say is, you don't need to FOIL, because the outside and the inside is going to cancel. So that times that, roots fly off. Square root of 3 times the square root of 3 is square root of 9, which is 3. Here's where it gets a little complex. Negative times a positive is negative. I times I is I squared. And then the roof flies off. Now what is I squared? Well, that's negative 1. So it's like there's two negatives. That's 3 plus 2, which is 5. Now, I'm not going to find all of these because I don't want to bore you to death, so I'm just going to grab that one and say, hey, let's find the modulus of V. Well, V is right here, so this is saying go to the right, the square root of 3, and go down the square root of 2, and find the length of the hypotenuse. Well, A squared plus B squared equals C squared. That's just 3 plus 2, which is C squared. So 5 is C squared. So I take the square root, and there it is. Now, again, just to save a little bit of time here, I'm not going to do both of these. How do you get the square root out of the denominator with these complex numbers? Well, I want you to notice, back up here, this had a bunch of square roots in it. But the answer did not. That's because if you multiply one of these complex numbers by its conjugate, you will never have a square root. So I'm going to take this one because it's the more difficult of the two. I'm going to start. I don't care about the top. I got to get the square roots out of the bottom. Now remember, I is the square root of a negative 1, so you can't leave an answer with I in the denominator either. But watch this. If I just multiply this by the conjugate, the top, there's no way out. I got to FOIL it. So that's 9 minus 21i minus 6i, and this is plus 14i squared. Let's clean this thing up. This is negative 14. Plus 9 is negative 5, and then these are like terms. So it's negative 27i. And down here, because these are conjugates, you can just So square root of 3 is 3. 7i times negative 7i is negative 49i squared, which is just 3 plus 49, because I squared is a negative 1. Negative 1 times negative 49 is positive 49. So that would be my answer. Now if there's a number that can go into all of these, then you should reduce all of these by that number. But obviously this one is stuck. That's it. That was a long lesson, but good luck on your homework.